We are going to discuss some control techniques for synchronization of inverter-based distributed energy resources. So just to give you the brief idea, nowadays, as we all know, we are talking about a lot of sustainable energy, renewable energy, and all the distributed or renewable energy sources are connected to the utility grid, or they feed power to the load by the help of usually power electronic converters. If it is a DC microgrid, these converters could be DC to DC converters. If it is a AC grid or microgrid, then usually we will have inverters. Now, once we have inverters, it is very important to understand how we control the inverter, because an inverter by itself will not have any physical law to follow. It will only follow the control technique that we decide. So it is very important that what kind of control technique we are going to work on. Accordingly, our inverter, which is supplied by any distributed or renewable energy source, will work. And therefore, this is very important to understand the different control techniques for inverter-based resources. Now, coming to the control techniques for inverter-based resources, it is equally important to first synchronize the inverter-based resource. Any generator in a system, be it synchronous generator or be it inverter-based generator, needs to be properly synchronized. And in inverter-based source, the synchronism takes place through the control. And that is why in this topic, we will mainly focus on the control techniques for synchronization of inverter-based distributed energy resources. That means we will discuss different control aspects that are used to synchronize. So we will discuss important concepts related to synchronization of distributed energy resources, particularly the inverter-based distributed energy resources. We will see the classifications, types, control methods, and how we can implement those. So, as we discussed in the title, we have to focus on the synchronization of a distributed energy resource. Now, first question comes: what is the synchronization, and why is the synchronization needed? So, the process of matching the voltage, the frequency, and the phase angle of one power source with the another is basically called synchronization. That means one power source is working in synchronism with the other power source. Take for example, we have a generator and the generator wants to connect to the electrical grid. Now our electrical grid is, as we all know, is 50 Hz electrical grid. So any generator which is coming online also has to produce 50 Hz. That is very obvious. If the frequency is not 50 Hz, then there will be circulating currents. So obviously we have to match frequency and then we have to connect. But that is just not the only thing. We also have to match the voltage magnitude. For example, if the generator bus is 13 kilovolt, 13.8 kV, let's say, our generator has to produce 13.8 kV, 11 kV or whatever. If it is a local distribution system, 400 volts, our generator has to produce 400 volts. We cannot connect a 11 kV at a 400. Otherwise, again, there will be large circulating currents. Likewise, if you see the wave equation of an AC waveform, in an AC waveform, the equation is given by Vm or root 2 times Vrms sine omega t plus phi. And the phi is the phase angle. Now, phase angle plays a very important role. Because you know, in an AC system, power can flow for the same voltage, for the same frequency, just by shifting the phase angle. So, phase angle also has to be synchronized. That means if you can recollect a phasor form, if you have a phasor that represents the bus voltage where an incoming generator is to be connected, then the phasor of the incoming source has to match the phasor of the bus voltage. Now, once you match the phasor of the incoming generator with the phasor of the bus voltage, both are same. Now you can connect them. If you can connect them, that means the internal voltage of a source becomes the voltage of the terminal voltage, which is the bus voltage. So the internal voltage and the terminal voltage are same, and there is an impedance in between, which is usually the internal resistance of a source. Now the internal resistance of the source will see zero voltage difference across it because the sources are properly synchronized. If the proper sources are properly synchronized, the voltage difference is 0, and we connect the source to the bus, there is no voltage difference. So delta V is 0, V by Z becomes 0, the current becomes 0. So no current flows to the system. And this is a safer way of integration. Now that's not the end of the story. If we just connect it like this, then obviously there is no current flowing. If there is no current flowing, then there is no power flow. So P and Q are 0, active power and reactive power are 0. So then what we have to do? Then after the synchronization is achieved, we have to do something to increase the power to the desired value, be it active power, be it reactive power. So the control can be divided into two stages. First is the matching of the voltage, frequency and phase, and second is to change it to an appropriate level to get the required voltage. Now, so the point is, if we do not match initially, then there will be, once we connect, because the internal resistance of a source is very small, as you know, and if the voltage, frequency, phase are not matched, then there is a delta V, and V by Z, you know, is the current. Numerator, there is a quantity, and the denominator Z is a small number, and therefore the I becomes very high. So a large inrush current. So the technical term we say is inrush current, and that inrush current can lead to equipment damage. Therefore, it is very important to have a proper synchronism. So synchronism is needed to ensure the safe operation, to avoid inrush, to maintain stability. Sometimes what happens if it is not synchronized properly, then a large amount of P and Q may be injected into the network. The network may see a very large inrush of active or reactive power, and the network may, some kind of instability problem may arise. So therefore, to ensure the safety of the device itself as well as the stability of the power system, we need to have proper synchronism. Once we synchronize it, then we need to inject current as to meet the desired power level. So to understand this concept for an inverter-based source, that how do we actually synchronize this, we have to first understand the basic concept that we all have read in our basic engineering, that any source can either be a voltage source or it can be a current source. Now, what is a voltage source? What is a current source? By definition, by the term itself says, a voltage source delivers a constant voltage. You have ideally internal voltage is constant. A current source delivers a constant current. Now, here comes an interesting question. If you can allow the participants to unmute for a second and then answer this question. We have an inverter-based source. For example, we have a rooftop. Let's say we put a rooftop PV at our homes or academic buildings or industrial buildings, wherever. And then obviously we have to use an inverter to connect the renewable source with the grid. Now that inverter-based source is a current source or a voltage source? Can anyone just answer maybe in the chat box or by unmuting? The moderator can tell what kind of answers you are receiving. We'll take just few seconds here and then we'll continue. Any of the participants? We have the question is very simple. We have an inverter, and whether the inverter is a current source or a voltage source. If you do not have answer at this point, then this presentation will give you the answer in detail. But if you have any answer at this point, please type in the chat box and the coordinator can tell me if there are any answers. So the question was whether an inverter is a current source or a voltage source. To understand this thing, we have to understand the types of inverter-based resource.
Sir, one participant is saying voltage source.
Okay, that's a good answer. Thanks for the response. So definitely, we all feel that an inverter can be a voltage source because we have a DC voltage and it can convert to a AC voltage. So we can have a voltage at the end of the terminals of the inverter, and that's why we can say it's a voltage source. But that's not the complete picture. The complete picture is the inverter will behave either as a current source or it will behave like a voltage source buys control. Take for simple example, let's say, what is the voltage that we get at our homes? The voltage that we get at our homes is like 230 volts. Can we change it? No. If I have a small generator, let's say at my home, and I put it in the wall socket, can I change the voltage of the wall socket? No. The voltage remains fixed because the voltage is coming from a grid, and behind the wall socket, I have a very large grid. We call it infinite grid. While the generator that I have at my home is usually a small generator. Let's say a single phase, for example, just take for example, a battery inverter, a single phase battery inverter, let's say. Now think about this, a small entity cannot change an infinite system, cannot change a thing which is very large, which is very strong. So the voltage will still remain 230 volts. But ideally a voltage source can have its own voltage. So then if I have to connect a source which is with me in my home to a wall socket, how would I connect? I have to ensure that its voltage is also 230 volts only, output voltage. Then how do I vary the power? By changing the current, because I can inject current into the network. But still the voltage will remain 230 volts, which is the grid voltage. So that means this source that is there in my home does not have the capability to regulate the voltage, but it has the capability to regulate the current. And that is why this source will behave as a current source. So by definition or by theory, it may produce a voltage, but it will be, its behavior will be like a current source. I hope this is clear. So think about this now. Let's say we put a rooftop solar photovoltaic panel at our homes, and we use an inverter and we connect it to grid. Again, the grid is very strong. We cannot play with the grid voltage. Whatever is the grid voltage, our output should match the grid voltage. That is what synchronism is. And then how do we change the power? By changing the current injection into the network, by changing the magnitude of the current, or by changing the phase angle of the current, so that the power flows into the network, so that now this source actually behaves like a current source. Although it can produce an output voltage, but its mode of operation is called a current controlled mode. Okay. Such a source is called a grid following or grid feeding source. That means there is a point of common coupling. There is a point where it is connected. At that point, the source has to operate in synchronism with the grid. It cannot have any other voltage, magnitude, frequency, phase. Or if it is a DC system, it cannot have any other voltage. So first of all, the output voltage has to match with the grid voltage. And therefore, it is called a grid following or grid feeding source. Or in our case, grid feeding or grid following inverter. And how would this inverter inject power? As I told, by changing the current that is injected, and therefore it's called a current control source, and therefore it behaves like a current source. But think about a different scenario. The same PV, the same inverter, but there is no grid. It is just feeding local loads. For example, in all our homes, we have inverter. Whenever there is a power failure, our inverter comes in and it feeds power to our home appliances, just like lights, fans, and all. Now, these appliances, light, fan, these all appliances, what do they need? They need a regulated voltage to be supplied, right? And what will be the current they will draw? They will draw a current depending on their impedance, simply V by Z kind of thing. So now the inverter output, which is there at our home, the inverter output should provide a regulated voltage. Why? Because if the voltage is not regulated, then our home appliances may not work satisfactorily, be it a fan, be it a light, or be it any other thing. So that means now the inverter's task is to regulate the voltage, not the current. Current will be automatically drawn depending on the load. If we turn on one light, there will be some current. If we turn on two lights, the current will double. If we turn on two lights and a fan, the current will further increase. So now the current is variable, is not controlled, but the voltage is in your hands. Now our household inverter that is there, it can produce output voltage 230 volts, 220 volts, even 240 volts, doesn't matter, because it is completely working independently. So now it is behaving like a voltage source. Its first task is to maintain that voltage. So it is now behaving as a voltage source. Such an inverter is called a grid forming. That means it is forming its own grid. It is creating its own voltage reference. It is creating its own voltage. So it's a grid forming or an autonomous inverter. So there is a clear difference between the two schemes. In one, where we have to operate in synchronous rhythm with the existing voltage, there the source has to be controlled in such a way that it behaves like a current source. It cannot play with the voltage. It doesn't have the capability to play with the voltage. While in the second case, there is no grid. You are working autonomously. For example, let's say you are working in a rural electrification and you have to electrify a village where there is no grid available. So the inverter itself has to produce the desired voltage. That becomes a grid forming inverter. Here it is a voltage controlled or a voltage source. Now there is again very interesting question. Let's say we have a rooftop. Let's say we have our own academic building, our institute building, whatever, office building. And on the top of the building, let's say we have put a array of PV modules. We have a rooftop PV generator. Now that rooftop PV generator is connected to the grid, and whatever is the solar irradiation, accordingly the rooftop PV generator feeds power to the grid. And also we can consume locally in the same building. That is also possible. Now, but then there is an interesting problem happens. Let's say the grid is out. If the grid is out, that means there is a grid failure. There is we are not getting any voltage from our distribution company. Our rooftop PV, in a common layman's sense, if we see, we have a rooftop generator at our home or building or wherever we have placed the rooftop generator. There is a rooftop PV. We have an inverter. It should produce a voltage and it should at least give supply to some of the loads, if not all, in the same building. Imagine we have a rooftop at our home. The grid is out. We would expect the rooftop to generate a voltage to feed our home, but that doesn't happen. As soon as the grid is out, the rooftop PV generator also turns off automatically. Now it's a very interesting scenario. You have put a generator at your academic or industrial building, wherever. We expect, okay, even if there is grid not there, at least we have some generator. But that generator will not produce power. It will also turn off. Why? Can someone think about it? You have a generator, but it will not work. Again, just few seconds. Anyone can either type or unmute and say the answer. It's a very interesting thing. I hope you are getting the problem. That there is a PV, but it will not produce power. There is PV generator, there is complete sunlight, everything is there, but it will stop producing any power. It will not produce any power. Why? Any answers? So it's a very interesting thing. As I told, the inverter is categorized into two types, whether it is a grid following inverter or it is a grid forming inverter. Now, most rooftop PV generators or the inverters that we have, those inverters are usually grid following inverter. As I told, they are connected to the grid at the point of common coupling where the grid voltage is constant. Sorry, is someone saying anything?
Reference from the grid actually. If grid is not working, it's a reference of voltage.
Yes, that's a very good answer. So the point is the inverter takes reference from the grid. What is the meaning of that reference? The meaning of that reference is the inverter is behaving like a grid following inverter. That means it needs to have a voltage defined at the point of common coupling. Where is that voltage? How much is that voltage? At that voltage, as I told, it will behave like a current source. It will inject a current to achieve the maximum power MPPT that we all know. But if the grid is out, there is no voltage. That means there is no voltage to synchronize with. As I told, any local generator has to synchronize with the grid. So there is no reference with which it can synchronize. And because there is no reference with which it can synchronize, its controller will turn it off, because we are not getting any reference. We don't know what is the voltage. We don't know at what voltage to synchronize it. We don't know what is the current that we should inject. It's better for safety, turn it off. So the inverter will turn off even if it is complete good bright sunlight. So the PV will also stop working. So that is why it is important to understand how a grid following inverter works and how a grid forming inverter works. So the grid following inverter is basically, as someone just answered, it needs a reference. It needs a reference, and the reference is basically the bus voltage to where it is connected, and that is called the point of common coupling. So it is connected at the point of common coupling through a control mechanism. It is controlled. Okay. So for example, if you see this figure here, we have a distributed energy resources and we have an inverter. For example, a three-phase inverter, a single line diagram is drawn. We always connect an inverter with a filter to filter out the harmonic components. And let's say we have a grid, the bus voltage is given as V bus. So this source, that means the source, the inverter and the LCL filter, this as a single unit is our inverter based resource. That has to be connected to the bus, V bus, in a synchronized manner. So how do we synchronize? We have to first get the bus voltage. What is the bus voltage magnitude? What is the bus voltage frequency? What is the bus voltage phase angle? Once we connect to that voltage, then to change the power, we can change the current as shown here, IL or IO. Once we change the current, the power flows. And usually for a PV, there is an MPPT control which maintains the maximum power and all. So how do we do this? As I told, if you electrically see this source will behave like a current source. So you have the grid, you have the point of common coupling, VPCC we call. Here it will be connected like a current source. Electrically it will be modeled like a current source. And how much current it will generate, how much current it will inject into the network, that reference current is actually given by a controller. So we need to have a controller. What this controller does is, you give a set point, you give a reference. For example, let's say we want X kilowatt and X kVAR from the inverter. So we give a reference, P star, Q star, the active power reference and the reactive power reference. Now this active and reactive power reference will be converted to a current reference and the current reference will be given. So basically now what happens, first of all, we have to sense the phase angle of the bus voltage. Now you see in terms of a phasor quantity, we have a phasor, we have a bus voltage phasor, and the current phasor can be in same phase, can lead, can lag. If it is in same phase, it will inject only active power. If it is in leading phase, it will inject reactive power. If it is lagging, it will basically draw reactive power. So the point is, we have to first sense the phase angle of the grid voltage. How is that done? It is done with the help of a device or a block that is called a PLL. In short, it is called a phase locked loop. What is the task of this phase locked loop? It will lock where its output matches with the angle of the bus. Then this output you will know, okay, fine, this is the bus voltage. Once we know the bus voltage angle, then, okay, fine, now we know the bus voltage angle. So we have to inject a current which can either be in the same phase, or it can be lagging, or it can be leading, depending on the active and reactive power set point that we want. Sometimes we may have a fixed set point P or Q, P star, Q star. Sometimes we may have a DC voltage set point VDC star and Q star, or sometimes the P star, Q star can be a function of the grid frequency, grid voltage. Basically, it's called a grid support function. That means if the grid frequency is coming down, then you inject more power to support the grid. If the grid voltage is coming down, you inject more reactive power to support the grid. So then the P star, Q star, they also become variable of the grid condition. Such inverter control is called a grid supporting control. So it's basically the same thing, that you have to control the inverter in a grid connected mode, synchronize at the common point of common coupling, inject a current in the desired phase to get the required active or reactive power. Now, this is achieved by a controller. So everything, as I told, for an inverter by itself, it doesn't have any physical law to follow. It will only be governed by the control algorithm that we use. So for an inverter, it becomes very important what is the control mechanism. And that control mechanism is usually, for a three-phase inverter, carried out in D and Q axis domain, not the ABC domain. Okay. So you see here, what is this thing? We have a phase lock loop, and it gives me two quantities, VD, which is the D axis voltage, and VQ, which is the Q axis voltage. Now, what is the VD, D axis and Q axis? Let's see this. We have a Parks transformation, which converts ABC three-phase quantities like Vm sin omega t, Vm sin omega t minus 2 pi by 3, Vm sin omega t plus 2 pi by 3. We have three-phase quantities. Now, these three-phase quantities are continuously time varying. To design a controller for a continuously time varying quantities, it's a little bit difficult. For example, you see, we all do. So for example, let's say motor control. We say our reference speed is 1000 RPM. We have to control the motor at 1000 RPM. So that 1000 is a fixed number. As long as the reference is a fixed number, like a DC, not time varying, you can suitably design PI controllers, the proportional integral controllers for such systems. But if it's a time varying system, like Vm sin omega t, Vm sin omega t minus 2 pi by 3, like this, then designing of a suitable PI controller becomes difficult. So what we do, we simply use a Parks transformation that converts ABC domain to D and Q axis domain. So we have now two phasors which are D and Q axis, and now we try to match the DQ axis with the ABC axis. And we try to match in such a way at that point when the D axis is completely aligned with the A phase axis. That means now we know, okay, how much is the phasor. That will give me the angle, what is the bus angle. So what we do basically, we use a phase lock loop or a PLL. So the first thing that comes in a grid following inverter control or a grid following inverter synchronization is a phase locked loop. What this phase locked loop will do, it will take the voltage VABC and it will convert to VD and VQ2 quantities using the Parks transformation. Ideally, there are three quantities, VD, VQ, 0. So V0 is usually 0. So we talk about mainly VD and VQ. Now, when it is completely aligned, when the A phase axis is completely aligned with the D phase axis, what happens? Our voltage phasor completely falls in the axis of the D phase. That means the perpendicular component, which is my Q axis, this becomes 0. So how do we know that we have properly locked the phase? We have a controller, again a PI controller, that will lock the phase in such a way that the VQ becomes 0. So what happens? We have ABC to DQ conversion, which is called the Parks transformation. This ABC to DQ conversion will give me VD quantity and VQ quantity. And my target is to make this VQ quantity as 0 so that I know that my D axis is completely aligned with the A phase axis. Now there will be an error. This error will be given to a PI controller. Very simple PI control architecture. This will give me a signal delta omega, which is the variation of frequency, because in a system you cannot have exactly 50 hertz always. Even if you have 50 hertz, you have to vary the in transient you may have to vary the frequency a little bit, because sometimes you may have to increase the angle or decrease the angle to get the desired angle, and then you have to bring it back to 50 hertz. So that is done by this delta omega signal. It is added to the nominal frequency, which is our 2 pi 50 radian per second, and the output is omega, which is the frequency. So with this omega, we'll know what is the grid frequency, and the integration of frequency gives us the angle. So this is the theta PL, this is the angle. So our controller will depend on this theta PL. Okay, this is my grid voltage angle. And we represent in the phasor form V angle delta. This is our grid voltage phasor angle. Now we know the grid voltage phasor angle. Then we have to develop this overall control scheme to get the power control P and Q for a grid following inverter. So this is the basic of it. Then we'll go to the details, mathematics, analysis and all. So if anyone has a question at any point, please feel free to discuss. So in summary, the point is we have an inverter, which is a grid following inverter, which is connected to the point of common coupling. It has to be controlled. It has to be controlled to get the desired P and Q. That is done by help of a controller. The controller controls the current that is injected by first taking the voltage reference of the grid, knowing what is the angle of the grid voltage, and then the current angle is accordingly adjusted, lagging, leading, or in phase to inject the P and Q. That is the overall philosophy of a grid following inverter. The second, as we discussed, is a grid forming inverter. Now again, you see that the system diagram remains the same. You have a distributed energy source, you have an inverter, you have the point of common coupling, filter, and everything. But the major difference is there is no grid. Here, rather, what we have is local load. Here, if we have local load, then the local load will demand a constant voltage, V bus. So the bus voltage has to be controlled. If the bus voltage has to be controlled, voltage source. So now the control mechanism will completely change, and the same inverter will behave like a voltage source. So now this is a voltage source. Now the point is, it is behaving like a voltage source. That means it is controlling its own frequency phase angle, Vm sin omega t plus phi. All the three variables, Vm, omega, phi are variable. There is no grid. So it can produce its own frequency, it can produce its own voltage, it can produce its own angle. And that is why, take for example our home inverter. When there is power cut and our home inverter starts, it may produce 200 volts, 210 volts, 220 volts, 230 volts. It may produce sine wave, it may produce square wave. Sometimes you must have heard, particularly the old inverters which were there. As soon as the power goes in our home and the inverter starts, we get a humming sound from our fans and lights and all. Why? Because the inverter is not even producing a sinusoidal waveform. It is producing a square waveform. It's a completely independent source. It is producing its own voltage. It is controlled as a voltage source. So that is the grid forming inverter, the second case. So we have almost covered half an hour. In the remaining 1 hour, we'll discuss the control technique or the synchronization techniques for both grid following and grid forming inverters. As we discussed, the basic control philosophy for a grid following inverter is the use of a PLL or a phase lock loop. A PLL, as we discussed, works like this. It converts ABC to DQ and it tries to maintain the Q axis quantities as 0. Now, D and Q is just a transformation. This transformation is a mathematical transformation. Now, for example, in simple terms, if I tell you, we control the RMS voltage. RMS is just a number. If I say no, we control the peak, that is also fine. If you control the peak, automatically RMS is controlled. Or if you control the RMS, the peak is automatically controlled. So these are just mathematical manipulations. And mathematical manipulation is in our hand. We can do any kind of manipulation. For example, let's say our RMS voltage is 230 volts. We say, no, I am not looking at the RMS. I am looking at 2 into RMS, 230 into 2. Again, just a mathematical number. The system will not change. If I control RMS to 230 volt, it will work. If I control 2 into RMS at 460 volt, again everything will work the same way. Nothing will change. So mathematical interpretations are in our hands. So this conversion from ABC to DQ, there are different ways to do it. Some may say, okay, we can align the voltage along D axis. Some may say that we can align the voltage along Q axis. There can be different variations of it. But in principle, the things remain the same, that, okay, one axis will be aligned, one axis will be zero. What is this mathematics here? You see, there is a Parkes transformation matrix that is given ABC to DQ. This is a block. This block converts ABC to DQ0. That is done by this Parkes transformation. You take UA, UB, UC as three inputs, the VA, VB, VC, the three phase quantities, and using this matrix, we convert to DQ0. Now there are two formulas written. Both of them are different. This basically shows that the two matrices are different. What this means is that, just one second. Okay. What this means is that you can have two formulas. Actually, as I told, we can control the VD or we can control the VQ. We can control the VD or we can control the VQ in any way we want. So let's say, as I talked about VM, the peak or the RMS or the 2 into RMS, they all are in our hands. They all are just mathematics. Okay. So what mathematics we choose is in our hand. We are controlling the peak or we are controlling the RMS. It is in our hand. So accordingly, the formula can get changed. The point is we have to convert to two DC quantities which are either in phase and the second is in quadrature. And these two quantities, sorry. So these two quantities, VD, VQ, we can use different kind of mathematics. So these are two well-known approach of Parkes transformation that we use, VD, VQ, and second VD, VQ. You can use any one of these. The point is the ABC quantities have to be converted to D and Q. Now, as we discussed here, ABC quantities to D and Q. Now, if you see these matrices properly, in the ABC to DQ, there is a theta variable. What is this theta? This theta is basically omega t. And this theta is coming from the PLL. So the task of the PLL is to provide this angle, and when this angle theta is properly achieved, what we get? We'll get VD as the magnitude and VQ as basically 0. So first point of synchronization of grid following inverter is that we have to understand how a PLL works. And the PLL is like this. We use the mathematics of Parkes transformation. The Parkes transformation give you, depending on the type of formula, either the RMS of the phase or the RMS of the line to line or the peak of the phase. Doesn't matter which quantity you use. As I told, we can control any one, the others will automatically fall in place. Using this, you can control all the quantities that we can control in an AC system, just like P, Q. In an AC, we know power is basically VI conjugate. So we know in an AC, we have three phasors. We can have three phasor quantities. Here also we have two phasor quantities. The in-phase quantities will always give active power. The perpendicular quantities will give reactive power. So if we just multiply the same way, ID in this form, ID plus JIQ. So we take the conjugate because power is VI conjugate. I conjugate is ID minus JIQ, and just like we do power is VI conjugate, we multiply VI conjugate, we can get the power. Now in different literature, we may see different kind of relation of the power, because we see this transformation is not a fixed transformation. There can be different kind of transformations, as like two examples shown here. But the point is they are all DC quantities. VD is also constant, VQ is 0. So if we use this approach, different kind of relations, and accordingly our formula of power may have different coefficients like this here, 3/2 or not just 1. But the point is, active power is basically the multiplication of in phase quantity. That means Vd into Id plus Vq into Iq in phase, Q with Q, D with D. Likewise, reactive power is basically the multiplication of perpendicular quantities. Just like we have in a simple AC phasor, we have in phase current and we have the perpendicular currents. If the current lags or leads by 90 degree, it gives reactive power. If the current is in phase, it gives active power. So we have VQID, Q multiplied by D, and accordingly D multiplied by Q. Now, in simple terms, if your PLL is working fine, then this VQ will become 0 due to this action. If the VQ becomes 0, so you can put 0 here and you can put 0 here. So P can be just VDID and Q can be just minus VDIQ in simple terms. So the point is, we can control the P and Q, the active power and the reactive power, by controlling the D axis currents and the Q axis current, ID and IQ. Because as I told you, see, if I put VQ0 here, what I get? Active power is simply VD into ID multiplied by 3/2. Or if you neglected the 3/2 part, it is just VD into ID. Now VD is the grid voltage. As I told, the grid voltage is constant. It's just converted from ABC to DQ. If it is converted from ABC to DQ, the grid voltage D axis is constant. So this is constant. So what is the only variable left? The only variable left is ID. The D axis current is variable. Likewise, if you talk about the reactive power, J times minus, if you make VQ 0, you will get VD into IQ. Now again, VD is the grid D axis voltage. Grid voltage is constant. So this is a constant. What is the variable? IQ. IQ is the variable. So by controlling the IQ variable, we can control the Q, the reactive power. That is what is shown here. If you see this figure, there are current set points, ID star, IQ star. So we have been talking about this, that the inverter actually behaves like a current controlled source or a current source. So that means the current, how much is the current to be injected, is controlled in two axes. One is the D axis and one is the Q axis. By giving it set point, okay, how much, this much the current, D axis and Q axis. Again, that D axis current and Q axis current reference that we get is converted to ABC to generate the PWM, because you know, an inverter is controlled by the PWM. So let me just look at the time. Accordingly, we'll see how much in depth we go, but we will not go into the mathematics of all. So as I told, the grid following control design will be like this, where you have two objectives. Either you control the active and reactive power. But when do you control the active and reactive power? When the DC side is regulated. For example, a battery, let's say. A battery output voltage is regulated, X volts. So the DC link voltage is regulated. In that case, you can control the active power and reactive power. Second case, if you have a distributed energy resource like a PV, and you know PV is variable, the DC voltage is not constant. In that case, the same way you can control DC voltage and reactive power, because control of DC voltage and control of active power are basically the same. Why they are same? Because both are energy. The DC voltage is also related to the power flow. If the more power comes from the source and less power goes, the DC voltage will rise. If the power from the source is less, more power goes into the network, the DC voltage will come down, the DC voltage will fall. So that means the DC voltage is related to power, and therefore whether it is power control or whether it is DC link control, they are related to same. So therefore for both DC link control and power control, we control this ID variable, and for the Q control, we control the next variable, which is IQ. All right. So how do we do this? Now comes a very basic concept. The basic concept is, you see here, we have the point of common coupling. We have denoted it by a variable V bus. If you make a small assumption that we have a LCL filter, usually the second one is very small. So if we neglect the drop in this second inductor, then the output voltage of inverter can be treated as the voltage across the capacitor, VO. So the VO becomes same as V bus. Okay. Now VO becomes same as V bus. We can assume that this drop is negligible. If this drop is negligible, VO can be treated as same as V bus. Now, how much will be the current that will be flowing through the inverter? The current will flow. To change the current, we know we can change the inverter terminal voltage, because you know current always flows by the difference of the voltage. So we have to create a voltage difference between this terminal, which is the V inverter, and the V output. This voltage difference has to be created to have the current flow. So how do we create? How much voltage difference do we create? We create a voltage difference by a simple. You can have a mathematics of this inductor. This inductor mathematics, we all can derive the equation. It's very simple. How do we write? We write L di by dt, the voltage across the inductor, minus Ri is equal to the voltage difference. So accordingly, we have this equation, and I'm not going into the equation details because of the time constraint and all. But the point is, we have these equation theoretically in the ABC domain, the three-phase time varying quantities, ABC, right? The three phases. Those three phases we convert to Parkes transformation, because we have to convert to D and Q axis. Why do we go for D and Q axis? As I told, because they become constant or DC quantities, the control becomes easy. We can control. We can use a PI controller with it. Now, what we do, if we develop this algorithm, okay, if we follow with this equation, we find that we can develop a controller which is UD variable coming from a PI controller. We'll not go into the details of the mathematics, but the point is we can have a variable UD which comes from a PI controller, and accordingly this controller can tell what should be the terminal voltage here, V inverter. So we can find this should be the VD inverter or VQ inverter, and accordingly we can have a this is the voltage VD inverter or VQ inverter we want. What this voltage VD inverter VQ inverter will do, because the bus voltage is constant, accordingly this output voltage is constant. If this output voltage is constant, this voltage we can change to change the current. So our objective is to change the current to meet the power flow. So see how the control goes. Our first objective was to control the P and Q, the active and reactive power. It translates to the current, as we are saying that it behaves like a current control source or a current source. So our objective becomes to control the current. Now the question comes, how do we control the current? That current will vary as per this inverter voltage. So then we go to the next step. The next step is that we have to control the inverter current. So our controller has to design in such a way, eventually the controller will tell us what should be our inverter voltage. Now, if we know what should be our inverter voltage and we know our DC voltage, we can calculate what should be our modulation index. You know, because the AC voltage in an inverter and the DC voltage in an inverter are related with the modulation index. So our controller will tell, okay, we need this much inverter voltage. We know the DC voltage. Accordingly, we can calculate the modulation index and we can generate the PWM signals for the inverter. So the overall control diagram will basically look like this. Again, I'm keeping it simple, not going into details. We have the first control, which is either the Q control with P control or Q control with VDC control. So you have VDC compared with the reference, compared with actual. There is a controller which gives me the current in the D axis. As I told, for the reactive power, it will give me the current in the Q axis. Now, all quantities are theoretically ABC quantities, time varying quantities. How do we convert those time varying quantities to DC quantities? By the Parkes transformation, ABC to DQ. As we discussed in the ABC to DQ transformation, we will need a theta. How will we get this theta? This theta will come from the PLL. So at the end, our PLL gives us the required angle. Now we get the required current reference. Okay, this much current we have to inject. As I told, how much we inject the current, it will depend on what is our terminal voltage. So finally, we will calculate by a controller what is the magnitude of the terminal voltage that I want. So I have VD inverter and VQ inverter. Basically, this inverter voltage here, this inverter voltage converted to D axis and Q axis. Okay. So we have VD inverter and VQ inverter. And then we can convert it to modulation index, MD and MT, the modulation index in the D axis and the modulation index in the Q axis. And the modulation index then can be converted to, again, inverse Sparks transformation. So here we have Sparks ABC to DQ, then we have inverse Sparks DQ to ABC, and we can convert it to modulation index in the A phase, B phase, C phase. So we'll have 3 time varying modulation indexes. Accordingly, we can use the PWM generator to generate the PWM signal. So this is the overall inverter synchronization technique for a grid following inverter. Now, this is not the only technique to do it. There are many other ways to do it. So as our focus is to understand the various type of synchronization techniques, we'll discuss one more for grid following, and that is called a unit template. It is very simple. So our point is to have current in phase with the voltage to generate active power, and current perpendicular to the voltage phasor to generate reactive power. So what we do, we have the time varying ABC 3 voltage signal, which is the bus voltage reference, V bus. Now these 3 bus voltages, VA, VB, VC, if we can divide them by their peak, then we'll get 3 waveforms whose peak will be just 1 and bottom side it will be -1. So that waveform with a peak of 1 and -1 is called a unit template. So what we get a unit template waveform with a peak of 1 and -1 only. Now that peak of 1 and -1 is just a unit plate. It's a unit waveform. To that unit waveform, if I multiply a quantity of the current, let's say RMS value of the current or the peak value of the current. Okay. For example, we all know what is power. Power is VI cos phi. So what is VI cos phi? We know what is the I is the RMS value, the magnitude. Correct? So if we can multiply with that sinusoidal varying unit template, okay. Let me see. I do not have a waveform. Okay. So we have ABC quantities, divide by the peak, we will get the sinusoidal quantities of A, B, C with peak 1 and -1. Now, if that I multiply, okay, what should be my current peak? For example, 2 ampere, 3 ampere. Then I will get a current reference in ABC domain. So here, up to this point, we were discussing current reference in DQ domain. Now I'll get a current reference in the ABC domain. Similarly, this current which is in ABC domain and which is just multiply a unit waveform. This unit waveform is obtained. How is it obtained? It is obtained by dividing the voltage by its peak. Obviously, if we divide the voltage by its peak, then there will not be any phase shift. It will just a magnitude reduction to 1. If the magnitude gets reduced to 1, then there is no phase shift. That means this unit vector is in phase with the actual voltage. Now, if I multiply with the magnitude of the current, this current that I will obtain will also be in phase with the grid voltage, and therefore the power that I'll get will be active power. Therefore, we can say the in-phase inverter current synchronized with grid voltage controls the active power. On the contrary, if I can shift this unit template, this unit waveform by 90 degrees, then if I multiply with the current reference, I'll get a current waveform, sinusoidal waveform. This current waveform will be 90 degrees shifted with the voltage waveform, and then automatically that means that will control my reactive power. So the question comes, how do we get this unit template of in-phase 1 magnitude waveform and unit template of 90 degree shifted waveform? So for that, what we do, we calculate the peak of the voltage waveform. How do we calculate the peak of the voltage waveform? We know VABC are the voltage given by this equation, Vm sin omega t, Vm sin omega t minus 2 pi by 3, Vm sin omega t plus 2 pi by 3. You apply a simple mathematics, VA square plus VB square plus VC square. Do some trigonometric formulations using the relation sin square theta equal to 1 minus cos 2 theta by 2. If you do this, what we'll get is VA square plus VB square plus VC equal to 3 by 2 Vm square. That is the maximum. Vm is the peak value. That means I can calculate the Vm by just taking square root on this side and taking the coefficient on this side. So square root 2 by 3 Va square plus Vb square by Vc square. So my Vm can be obtained by this formula. That means when we are actually implementing this, I will have A phase voltage sample, B phase voltage sample, C phase voltage sample. Sample by sample, we will obtain them, square them, add them, multiply by 2, divide by 3, take the root. This will be a Vm quantity. This will be a constant Vm quantity. This Vm quantity, if we divide like this, actual voltage divided by Vm will give me the unit vector in A phase. Vb divided by the Vm, unit vector in B phase. Vc divided by Vm will give me unit vector in C phase. So like that, we'll get unit vectors, unit template sinusoidal varying quantities having peak 1 and bottom peak as -1. That with that, if we multiply our current reference obtained from active power control, just like the previous case, from the active power control, as I told, we can have a current reference, and the reactive power control, we can have another component of the current. Like that, we can control here also. So we can multiply this, so we'll get the current reference for the active power component. Now, what of the reactive power component? We have to again get a unit template which is 90 degree shifted. Now, how do we get a 90 degree shifted waveform? There are two basic approaches for that. One approach is the sample and hold method. That means you take a sample and hold it. For how much duration? You hold it for a T/4 duration. The T is the time period of the waveform. If we hold it for T/4 duration, what we get is a shifted waveform. Because now the sample will be shifted, every sample will be shifted T/4, T/4. T/4 means our waveform will be shifted by 90 degrees, 360 by 4, 90 degrees. Here we have to wait for T/4 duration. Another method is use a mathematical approach. Do some mathematical calculation, just like we have done here in this case. We can get the quadrature component by this relation. Negative of phase component unit template plus C phase divided by 3, like that we can get. So this will be a faster approach. So the point is, whatever method we use, we will have two unit sinusoidal waveforms. One is in phase with the actual voltage, one is quadrature to the actual voltage. Now, if we can multiply with the current references, the in-phase current reference and the quadrature current reference, just like we have done previously, the P reference minus P PI control will give me the in-phase current component magnitude or the peak. The Q phase, the reactive power control will give me the Q phase peak. We can multiply with the unit templates. First is so this P here represents the phase component and the Q represents the quadrature component, A, B, C. We have the phase unit template of A phase, B phase, C phase, multiply with the peak, we get the actual current reference in the in-phase component of the current, ABC domain. Likewise, we can multiply the Q reference to the 90 degree shifted unit template. We get IQA, IQB, IQC reference. We can add these two together to get the final A reference, B reference, C reference. Now we have the IA reference, IB reference, IC reference, three phases, because we have three phase quantities. In the previous one, we discussed about two phases, D and Q, because we by a mathematical manipulation, we converted 3 to 2. And because these two were DC quantities or constant quantities, we could use PI controllers. Therefore, ILD star compared with the actual ILD, we use a PI controller that gives a variable UD. On the contrary, in the present case, our current are time varying sinusoidal currents. IA reference, IB reference, IC reference. If we compare with the actual IA, IB, IC, we cannot directly use PI controllers. Why? Because as I told, PI controllers are suitable for DC quantities. They are not suitable for designing of PI controller becomes difficult for time varying quantities. Therefore, we have to use a separate control. So here, instead of using a PI control, what we use is a hysteresis control usually. So this symbol basically shows a hysteresis band. What is a hysteresis band is basically like this. If the current is within a band, so we have a reference, the solid line is basically the reference quantity, it's time varying sinusoidal, and we define a small band. If our current is within that band, then we don't change the switching state. As soon as it exceeds the band on the upper side or the lower side, accordingly we change which switch. In a inverter we have legs. In legs we have two switches, the bottom switch and the top switch. Which switch will turn on and which switch will turn on depending in which direction it is exceeding the band. Either it is exceeding above or it is exceeding below. Accordingly you see whether the upper switch is turned on or the lower switch is turned on. So the point is, we can have PLL or we can have a unit template for the control of a grid following inverter, basically to synchronize the grid following inverter, because the unit template will have the same frequency, same phase as the grid voltage frequency and grid voltage phase. So the point is, our grid voltage frequency as phase are obtained either by PLL or by a unit waveform or a unit template. This is about grid following inverter control and its synchronization. Next, we will go for grid forming synchronization. So we can take a couple of minutes here. If anyone has any question regarding the grid following part that we have discussed so far, please unmute and ask. We can take 2 minutes or 1 minute. If not, then we can continue in the second part, which is the grid forming inverter control. So as we discussed, for the grid forming part, our main objective is to regulate the voltage across the load. That means the V bus. What should be my V bus? Again, as we discussed, if we neglect the drop in the second inductor, we can say the V bus is almost same as VO. We have to control the output voltage. How do we control the output voltage? Again, depending on the load, whatever the current is being drawn by the load, the same current has to come from the inverter. And how will the inverter inject current? Inverter will again inject current by changing the inverter voltage, V inverter. So again, the control inherently is the control of this current IL, which is shown here. But the end objective is to regulate the VO, output voltage, not the P and Q. P and Q are automatically adjusted by the load. Whatever the load are drawing, the power will accordingly change. So our end objective is to control the output voltage. How do we control the output voltage? Again, the things will remain very much the same. We will have D axis output voltage, Q axis output voltage. One of them we try to make 0. PI controllers will give us the D axis reference, current reference, all those things. And what we will get eventually, we get VD inverter and VQ inverter, which is the inverter terminal voltage. And from this, we can again calculate the modulation index that we required. Now, here comes that question. If you see the previous case, the grid following case, for all the transformation ABC to DQ or DQ to ABC, we use an angle which is the theta PLL. How do we get this theta? We get this theta from the PLL. And how does PLL work? The PLL works by converting the bus voltage to D and Q, the grid reference. But when we talk about the grid forming mode, in the grid forming mode, there is no bus voltage, there is no grid voltage. So the PLL is not required. There is nothing the PLL can do, because there is no voltage in the first place. The inverter itself has to produce the required voltage. Now, as we discussed the example of our home inverter, whenever the power goes, our home inverter can produce any voltage, 210, 220, 230, 240. It can produce a square waveform even. Frequency can be 50 Hertz, 49 Hertz, 52 Hertz, doesn't matter. So basically the frequency is an independent quantity. It can produce its own frequency. What we do, we can just put a its own frequency reference, like shown here, omega n. So what this omega n does, it gives a constant frequency reference. Okay, the inverter will produce constant frequency. This omega n integrated will get theta. So here now the difference is that we don't need any PLL, rather we just integrate a constant frequency reference, and constant frequency reference will give angle, and this angle will be used for the grid forming inverter control. Now, what we have discussed so far is that the grid forming inverter works like this. Here, so far, we have not talked about the synchronization part, because as such, there is nothing to synchronize. There is no bus voltage. So how do we to whom we synchronize? So as such, there is no need of synchronization. But then we still need to study grid forming synchronization methods also. Why? Because what if there are two grid forming voltages? If there are two grid forming sources, one will say, no, I will produce 51 hertz. Other will say, no, I will produce 50 hertz. The system will get confused, because the system cannot have two different frequencies. The system will not work properly. So if there are more than two grid forming inverters in a system, then both of them also has to be synchronized. So therefore, the grid forming inverter synchronization comes by varying this frequency so that the multiple grid forming sources in a system work simultaneously. Again, there are a lot of methods to do so. One of the very simple method to do so is the droop control, in which we intentionally drop the frequency like the one shown in this figure. Why do we drop this frequency intentionally? Because at the end of the day, we want power flow between the sources. How does power flow? Power flows by changing the angle of one bus relative to the second bus. How would the angle change? The angle, because it's an integration of frequency, therefore we have to change the frequency to change the angle. So imagine a system like this. You have three inverters, 1, 2, 3. All three are working in grid forming mode, because there is no grid, they are operating in the microgrid. Now suppose there is a load here at bus 1. You know that current always takes the shortest impedance path, and the shortest impedance path is from the inverter 1 to the load. So the inverter 1 will supply power, maximum power to the load, while inverter 2 and inverter 3 will not supply any power. What this will do? This will lead to overloading of the first inverter and underutilization of the second remaining two. Now what do we do then? We have to forcefully inject power from the other two so that their powers match with the power of the first one. Resultant, combinedly they share the power, P load by 3 each one of them. So that means we have to intentionally vary the angle. How do we vary the angle? By varying the frequency, because angle is the integration of frequency. So that is what we do. As soon as the power changes, we change the frequency, so that, at a steady state we cannot have two frequencies. So automatically, if there is a frequency difference, there will be angle difference. If there is an angle difference, there will be a power flow. If there is a power flow, our controller that we have developed here, where we are intentionally changing the frequency, will retune itself so that at the end of the day, all the sources operate at a common point P at a common frequency F. So the frequencies are synchronized. So now the frequencies have deviated because of that droop control that we have implemented here. In this control, what we have done, as per the power variable P, the measured power, our frequency is changing. Now our frequency is changing, just like shown here in the results here. We have power and we have frequency. The frequency is dropped. Now, let's say a fourth inverter wants to come in. Let's say there are 4 homes. Each home will have a rooftop solar over it. They are operating in grid forming mode. And let's say a fourth home also wants to connect. Obviously, the fourth one also has to synchronize first. As I told, if it directly connects, it doesn't know what is the frequency. For example, here, if you see, the frequency is 49.95, let's say. If a new source comes, the fourth source comes, the fourth source has to synchronize. at this frequency. Ideally, we know the frequencies are 50 hertz. If the fourth source come and directly connect at 50 hertz, what will happen? A large amount of inrush current will flow. So because a large amount of inrush current will flow, it will damage the devices. So the fourth one, which itself is a new grid forming inverter, needs to be connected at the new frequency which the new inverter doesn't know. So we have to develop a control technique which somehow ensures the incoming converter is synchronized first, connected at the actual operating frequency of the network, and then it starts to inject active and reactive power. So that is where the grid forming synchronization is required. That means in a grid forming mode we have to synchronize so that first the power is the voltages are matched, frequencies are matched, and then the power starts to inject by the fourth source. That is the key objective in the grid forming synchronization. So in the grid forming synchronization, again, as I told, first case, let's say new source is coming, or even let's say one of these three sources are out due to tripping, due to failure, or whatever be the reason, and it wants to connect again. If it wants to connect again it has to be synchronized. It cannot just randomly connect. So it has to be synchronized. So the point is whether a new source is coming or the old source getting disconnected and getting reconnected has to be synchronized in grid forming mode. So again, there could be multiple methods. Within the time frame, we have around 20 minutes left. So in this frame, we will discuss two methods, and then we can have some question answer sessions. So there are two methods that we have worked on. These methods are named as output sync method and controller sync method. That means we are either synchronizing the output voltage, or we are synchronizing the controllers. How do we do that? Let's see. The first case is a simple case of grid forming inverter synchronization using the output sync method. So here in this one, I've used a simple approach of directly calculating the magnitude of the voltage and the frequency, not use the D and Q for the simplicity only. Now here, what we do, output sync, that means the output voltage has to be synchronized. So for example, let's say this system is like this. You have one grid forming source and the second grid forming source wants to connect. If the second grid forming source wants to connect, obviously there will be a circuit breaker in between. You have to connect the circuit breaker. How do you connect the circuit breaker? We'll connect the circuit breaker only when we ensure that the output voltage of the first source is synchronized with this PCC voltage. If it is not synchronized, and if we turn on the circuit breaker, because this, as I told, this LC2 is a very small inductor, the internal impedance of the source is small, a large amount of circulating current will flow and it can damage the device. That means we have to first match the output voltage VO with the PCC voltage VPCC. So how do we do then? We have to do something, because the PCC voltage and the PCC frequency both are variable, because the first source is operating in droop. Due to drop, the frequency is changing, the voltage magnitude is changing. So for example, as we have shown here, the first is the normal characteristic, is the droop. Let's say the source is operating at this point, which is given by a dot here. Now what we have to do for the second source also, the incoming source also, we have to somehow change its frequency. How do we change the frequency? We change the slope of this droop curve, shifting it upwards or downwards in such a way that initially what we want, that when it gets connected, the power should not flow. The current flow should be zero, just floating mode. It is called a floating mode. At floating mode, the power should be zero, the current should be zero. That means our characteristic should be shifted up and down in such a way that at zero power, it matches with the same frequency. So let's say this dot represents the frequency of the first source at any given operating point. Now, the second source characteristic has to be modified in such a way that the same frequency is obtained at zero power. So how do we do this? We modify the control a little bit. We use the additional signal which is named as delta omega. If you see here, this delta omega is what it is doing is it is trying to match the voltages in the d axis, and similarly in the q axis this voltage will be matched. One of them has to be 0, as we discussed. Anyone can be made as 0. So we compare with 0. We pass it with a PI controller, and the PI controller will make it delta omega. This delta omega, what it will do, it will shift the graph upwards or downwards in such a way that whatever was the previous operating point of the existing sources, at the same operating point is achieved for the new source at 0 power. You see the x-axis here, it is 0 power. That means if we achieve so, our voltage will be synchronized. That means if you see here, we have a circuit breaker. The voltage above and below the circuit breaker, VPCC and VO, these voltages will be synchronized. Once these voltages are synchronized, we can very happily turn on the circuit breaker, because now we know, if you see the circuit, VO is same as VPCC. Now there is no current flowing initially till the circuit breaker is open. That means the voltage across the capacitor is same as VO. So the voltage across the capacitor becomes same as voltage at the PCC. If these voltages become same, we connect the circuit breaker. The voltage difference is 0. There is impedance 0 by Z, gives no current, so no current flows in the system. The inverter is connected in the floating mode. But now it is just connected in floating mode. It is not giving any power. The power is 0. So how do we then inject power? Then we inject power by shifting this characteristic back to the original one. So as it's shown here, 1 to 2, the characteristics are shifted from graph 1 to graph 2 for synchronization, and from graph 2 to graph 1 for power sharing. So then we shift it back to the original case. But then that shifting has to be a very smooth, slow shifting. If we shift suddenly, then the system will see a sudden inrush of current. Again, that sudden inrush of current can lead to instability. So very slowly we have to shift this characteristic up back to this normal case. How do we shift this characteristic up? By making this delta omega variable 0. How do we make the variable delta omega variable 0? You see, we shift the input to the PI controller. The output of the PI controller is fed back to its input. That means the output of the PI controller will go back to its input. That means the PI controller will now make its own output 0. But it has to be made at a very slow rate. Therefore, we also use a gain in between, and we make this gain a very small gain. Now the PI controller will slowly make its own output 0. When it makes its own output 0, the characteristic will shift gradually upwards and upwards, and it will match the nominal characteristics. At that point, your power will also be shared. So the new source will contribute to the power sharing. Just illustrate this by the help of these figures. For example, initially they are not synchronized. First source, second source can start at any random frequency, any random voltage, so there can be instantaneous voltage difference. Like that, there can be frequency difference. If you see, initially one is at a different frequency, other is other frequency. Now what we do, we synchronize them. So here, as you can see from this, the frequency will start to match, and the frequencies match completely. At that point, we turn on the circuit breaker. If we turn on the circuit breaker and after proper synchronization, absolutely proper synchronization, there will not be any transient in the system. There will not be any power flow. This P will be absolutely 0. Here there is a slight perturbation, because when we do it experimentally, we cannot make absolutely synchronized. There can be very small variation, delta point, even a small 0.01 degree something, practical differences can be there. There can be slight perturbation, but not that much that can hamper the system. And then we gradually make the signal 0 so that they share power. So this is how the synchronization is achieved. So why it is named output sync? Because the output voltages are synchronized. VPCC and VO, these voltages are synchronized. Second case is instead of synchronizing the voltage, we synchronize the controllers. So I will not make it very complex. We'll keep it simple. Initially, what we do, we start the new source like a grid following source. Then in this case, we make two separate controllers. One is grid following controller and another is grid forming controller. What will the grid following controller do? The grid following controller will make this inverter grid following mode where the PCC voltage is taken as a reference. So it will be initially connected in the grid following mode. In the background, the grid forming controller is also running, but it is not used, but it is kept running. And we try to match the two controller outputs. So at the instant when the two controller outputs become same, when the two controllers become same, then we switch the controller from grid following to grid forming. So this is called controller sync match. So there can be two approaches. Either you first start in a grid following mode and shift to grid forming when the controllers are synchronized. Or as in the previous case, you start in grid forming mode only, you synchronize the voltage, connect the circuit breaker, and then shift the characteristics. So in the second case, the circuit breaker is always closed because now you are following the grid following mode. So you need to have the grid voltage available with you. Grid following mode, as I told, cannot work without grid. That means the PCC voltage has to be available. If the PCC voltage is available, that means the circuit breaker has to be closed. And the inverter will start in grid following mode, but then the grid forming control will run in background. Whenever the controllers become same, that time we shift. Now, what is the meaning of controller become same? In the grid following mode, we have theta coming from the PLL called the theta PLL. In the grid forming mode, we have its own theta as we shown here by the droop frequency, and the frequency is integrated to get the angle. So we have the inverter will have its own angle in the grid forming mode, which is running in background, which is not used. In the grid following mode, we have the theta PLL. Both are compared. When the angle becomes 0, it is shifted to grid forming mode. So you see now in the results case, you see here the instantaneous sinusoidal voltage waveforms are not shown because it's a grid following initially. The voltage are always synchronized. What is shown is the angle. One is the grid following angle and is the grid forming angle. Initially they are not same, but they are made same. How they are made same? Because in a grid following mode, you have a power set point P star. So you give a power set point P star. So initially it starts to feed power because it is already connected. It is already connected. It starts to feed power. The frequencies match. The angles match. When the angles properly match, that means now the controllers have synchronized. Whether the grid forming controller has been synchronized with the grid following controller, we can quickly shift the control mode. And therefore, if you see here at this instant T2, we have shifted the current, the mode from grid following to grid forming. And because the controllers were properly synchronized, again, you see the transient in the system is very small, negligible. This should happen. If there is a large transient, the system can become unstable. So you see the frequency, the power, there is no change because it has already achieved that power. So once we do the transition, there will not be any further change, but the mode of operation will change. After this point, it will operate in grid forming mode. So this is how we control the grid forming inverters. So with this way, I conclude my presentation for today. The simple concept is just a quick recap: two modes, grid following, grid forming, use of PLL or unit template for the grid following one. For the grid forming mode, either the output synchronization or the controller synchronization works. All right. So thanks for your listening, and I invite questions at this point if you have any.